So how would you describe in this example? And the way that this app is set up, it's taken the domain and the codomain and it's laid them on top of one another. So the black figure here is a figure in the domain. So that's the figure that is being transformed. And then the figure here in blue is a figure in the codomain. So that's the image. So our linear transformation is turning this black figure into that blue figure. So how would you describe in words what exactly this linear transformation is doing to this cat shape? What's happening here?
Is stretched and widened.
Okay.
What we said the other day when you have like a positive number, like stretches it or shrinks it, depending on how big the number is, and
Mm-hmm.
negative it goes to
It ends up reflecting it. Right, so let's take each of those two things that you just mentioned. There was a stretch that you mentioned, and there was also a what else?
you got like wider.
Okay, widened, widens. Let's make these in the same tense. There we go. So yeah, as you bring up, stretching is something we can do to a figure just by multiplying a vector by a scalar, right? That when I multiply a vector by, let's say 3 or something like that, then that tends to stretch out my vector by a factor of 3. If I were to multiply it instead by -3, what else would happen? If you multiply a vector by a negative scalar, it reflects, it flips. Flips over the origin. It doesn't look like there's any flipping happening here, because our cat used to be facing to the right, and the image is still facing to the right somehow. So at the very least, we can sort of observe that there's been a stretching going on here. In particular, let's take a look at the coordinates of this point on the original image of the cat was 3, 0. And then its image under this transformation, the corresponding point, ends up out here at 9, 0. So by what factor have we stretched this cat in the horizontal direction? Yeah, stretched by a factor of 3, it looks like. So we can actually kind of quantify exactly how much stretching was going on. And likewise, we might try the same thing for this point, 0, 2, except that its corresponding point isn't just a multiple of that vector, right? I've taken this vector and I haven't just stretched it, but I've stretched it and kind of moved it over a little bit too. But at the very least, the y-coordinate has also just tripled. Right? This point happens to be -2, 6. So it still looks like there's kind of a factor of 3 thing going on here. But it's not quite as cut and dry as it was in the horizontal direction. So in addition to that stretch, we also have this kind of widening going on here, that we've kind of taken the whole cat and pushed it over to the side, kind of like a stack of paper, just pushing it and it kind of slides over. Right? This is an action that we call shearing. Because it took something that used to be a square, so our cat used to fit into this little square shape. Whatever. And then when we transformed it, now suddenly it fits into kind of a skewed over parallelogram like this. So we call that a shearing action. But it turns out that linear transformations can only do so many different things to a figure. And what we're going to see in Chapter 5, when we get to Chapter 5, is that for any linear transformation, we are going to find a way to decompose it into which of these sort of basic linear transformation actions is it doing. Stretching is one of them. Shearing is another one. And in generality, let's list the remainder of the list here. So what can linear transformations do? Linear transformations can So we already saw they can stretch. They can also shrink. Right? If we decide to multiply a vector by a number between 0 and 1, right, then that'll be a shrink. So it can stretch and shrink. It can shear, that action of turning a square into a parallelogram, just sort of pushing it over to the side. Catherine also mentioned another thing that it can do. It can reflect. If we happen to be multiplying a vector by a negative scalar, then we're going to get a reflection in there. There's one other thing we haven't put on here yet, and that is linear transformation can also rotate. And again, each one of these actions has that basic linearity property that if I start with a parallelogram and I transform it, that the image is still going to be a parallelogram. If I decide to stretch this parallelogram, then maybe it gets longer in this one direction, but it's still going to be a parallelogram. If I decide to shrink this parallelogram, it's still going to be a parallelogram if I shrink it horizontally or vertically or whatever. If I reflect it, it's still going to be a parallelogram. If I rotate it, it's still a parallelogram. If I shear it, it's still a parallelogram. So all four of these geometric transformations are linear transformations because of that. And so then the question is, for a given linear transformation, which of these is happening? Because it could be more than one. I mean, this particular example has both a stretching going on in it, in addition to a shear. Let's look at another one. So stretching, shrinking, reflecting, rotating, and shearing. So there's one I left off the list. We'll see that in a second. Let's go to the example 1, 2, 2, 1. So adjust these matrix elements here. 1, 2, 2. Come on, slider. 1. That was a little tricky to tell because of the zoom angle. But can we say anything about what is happening here to the cat?
Rotated.
So it looks like there could be a rotation going on.
Yeah,
Rotate, reflect, and what else? Maybe a shear? Well, of these, I think we can be pretty confident that there's a reflection going on, because before the cat was facing to the right, but the image now is facing the other way. So there's some kind of a reflection going on here. Whether there's a rotation or a shear in here is a little less clear. Let me clarify a little bit more what rotations and shears end up looking like. Rotations and shears by themselves are examples of transformations that are supposed to preserve the area of things. So when I rotate or when I shear, I'm supposed to get something that has the same area as it had before. Preserve area. So in this example, because the cat that we end up with in our image is so much bigger than the cat that we started with, we can't just account for everything with a rotation and a shear, that we need a stretching going on in there. Actually, reflecting also preserves area, doesn't it? So the only one of the things on this list that can change your area is stretching and shrinking. Which means, in this example that we were looking at right here, because our image is bigger than the original, there's got to at least be some kind of stretching going on here as well. And there's some kind of reflection in there for sure. But whether there's a rotation or a shear is harder to say. And that's a question we're not going to get a lot of clarity on until Chapter 5. Because which of these things a linear transformation does depends on what are called the eigenvalues and eigenvectors of the transformation. It's a Chapter 5 topic, so we will revisit this in a lot of depth when we come back in Chapter 5 to it. There's one more kind of transformation I left off the list, because it is qualitatively quite different than the others. Let's take a look at this matrix. 1, -1, -1, 1. Whoops. Come on. Fine. Let's do it this way. All right. What has happened to the cat in this transformation? It shrunk. In fact, how much did it shrink? 100%. What is the area of its image? What would you say is the area of this thing that the cat has suddenly turned into?
1 or 0?
I would say 0. Why am I saying that this has an area of 0?
No shape.
It's got no shape. I mean, it's got no two-dimensional reality to it anymore, right? This transformation has somehow squished a two-dimensional object down into a one-dimensional object. So it squished my two-dimensional cat into a one-dimensional line. Needless to say, this doesn't happen very quote-unquote often with a linear transformation, and yet we can still do it, right? This matrix clearly is doing this. And this is an example of a transformation we have to add to the list called projection. If you've taken a course in vector geometry, either multivariable calculus or maybe a physics course or something like that, projection is also a big deal in vector geometry. So our complete list of things that linear transformations can do. They can shear, they can rotate, they can reflect, they can project, and they can stretch and shrink. Of this list, three of these transformations keep area the same, reflecting, rotating, and shearing. Stretching and shrinking is allowed to change the area, perhaps. And projection, what would you say projection does to area? Yeah, it eliminates it. It wipes it out. Because we somehow reduce the dimensionality of our object when we apply a projection.